Hi, in a previous video where I showed off this very cool DPS3003 power supply module, it's a complete lab power supply in a tiny little module like this. It's all fully self-contained, and I'll link in that video down below if you hadn't seen it. And it's a real cheap and easy way. It's like sub $25 delivered for this module, and you can turn it into a bench power supply. Just voltage in and voltage out. Fantastic. And here's the specs for the things, just as a recap. 6 to 40 volts input. It is a buck only, so you have to have an input voltage range, at least the dropout voltage greater than the output voltage range you want, the maximum voltage range you want of 0 to 32. So, for example, if you only needed like a 0 to 12 volt lab power supply, then you could get away with, say, like a 13, 14, say 15 volt input, something like that. So output current 0 to 3 amps, 96 watts, which I'm dubious about based on the the efficiency of the heatsink in this thing. But that's one part of this video. I want to characterize this now because so many people said that they want me to characterize this and see how efficient it is over various ranges. So that's what we're going to do. Anyway, very nice 10 millivolt resolution, 1 milliamp current set resolution, an adequate 0.5% plus 1 or 2 digits voltage and current accuracy. So what do we need to characterize this? Well, you can do it with your multimeters. This is where I've always said having 4 multimeters is very handy in your lab, because you can characterize not just modules like this, you can characterize your own design DC to DC converters. You can measure, you have 2 multimeters for the input, measuring the voltage and the current, i.e. the power going in to your converter, and then 2 meters measuring the voltage and current on the output, i.e. the output power. When you've got input power divided by output power, you can get your efficiency. So you can plot efficiency curves over various voltages and whatnot. So very handy to have 4 supplies, but we're not going to use multimeters today. We're going to use the Rigol DP832 power supply. This is like 0.05% class instrument, so it'll allow us to know the input voltage we're feeding in and the input current as well. Near enough. I'm not going to bother worrying about like the drop across the leads here. It's going to be near enough. This thing does have an external sense, so maybe I probably should take some wires around to the back. I don't know. Anyway, and we've also got the Rigol DL3021 DC electronic load. And electronic load, I've done videos on do-it-yourself electronic loads. You can build these really cheap. You don't have to spend, $500 for a commercial one like this. But once again, very accurate, 0.05% class, measuring the output voltage and the output current as well. And this one I do have the sense output. So I'm feeding that directly back to these terminals. I'm not going to worry about once again, the drop across these output cables here. It's going to be near enough because we're not going up to particularly high currents. Anyway, I've enabled the external sense there, and if you want to know what the dropout voltage is with no load anyway, I'm feeding 32 volts in and I'm getting a maximum of 31 volts out of this thing. So that's not bad. 1 volt dropout with no current load. By the way, in the previous video, I completely overlooked the fact that you could set the voltage and the current just by pressing these keys. I thought, I just went into set and, it was a little bit dicky to go in there and select your digit and all that sort of stuff. It was a little bit tedious, but you don't actually have to do that. You can, if you want to set your voltage, simply press V there and bingo, you've got your control. And it does seem to have maybe, like it goes in 10 millivolt increments there, it does maybe seem to have a little bit of velocity control. So I can turn that relatively fast, not as fast as I'd ideally like, but it's still quite usable. So very easy to set your voltage and current like that. So the user interface is really quite good, and it permanently displays your set voltage and current up the top, which I absolutely love. All power supplies should display set voltage and set current if possible, and also the input voltage as well, just so that you're aware if the input voltage is drooping or anything like that. Anyway, let's get on to the characterization. Now, there's two ways to get an efficiency characteristic curve of a power supply like this. One is to fully automate it, and these two instruments probably ideal for this task because they're both Ethernet LXI enabled. So if I hooked them up to network, the PC, you could write a script that outputted your necessary voltage from here. Of course, you'd be able to read back your input current as well, so you'd be able to read your input power going into your module, and of course you can control the electronic load, set it up for any constant current load you like, and then sweep it over there, and you can run various sweeping runs and get all the data points at basically 1 milliamp resolution, or whatever the resolution of this thing is. But unfortunately, even though you can fully automate these instruments here, this one down here is not. So you're going to have to actually set, turn the knob. Several from the same company who manufacture this, they do offer Wi-Fi enabled ones, Bluetooth enabled ones, and all serial enabled ones. So you can actually get digital control of these things. So you can actually, for virtually hardly any more cost, just like $5 or something extra, I don't know, $5-10 extra, you can get the wireless or serial enabled version of these modules. I believe in the bigger one. I don't think it comes, not sure if it comes in this smaller one. So yes, while I could semi-automate this thing by, like, I could sweep the load, for example, for a particular output current, and then I could get a characteristic curve of the load for each particular output voltage. You can get a whole set of characteristic curves and the efficiency at each point for each particular output voltage, and each adds over the sweep from 0 to 3 amp output current and all that sort of stuff. But hey, I'll just get a couple of ones, at like low output voltage, like 5 volts and then 12 volts and then 24 volts maybe. Those three characteristic curves might be okay for a 0 to 3 amp current sweep in, I don't know, 100 milliamp increments or something like that. Good enough. When you're taking these measurements manually, writing them down on paper, it takes time. So I'll just get fairly crude plot. It's going to be good enough. It's not like the characteristic plots are going to curve up like this and then suddenly go boom and then up. Like they're going to have a characteristic shape. Something like that. Typically, there's going to be a peak efficiency. So, I expect the efficiency of this thing, based on just some, temporary filling the heatsink on the back and stuff, it's going to be like greater than 90% at its peak. So it'll be interesting to see how efficient this is over the full range for a couple of input voltages and a couple of output voltages. So I just wanted to show you what the noise looks like here when you go from no load, which we've got at the moment, basically 20 millivolts peak to peak there, and we actually switch on the full 3 amps at a 24 volt output. There you go, it jumps up to like 110 millivolts or thereabouts. So it ain't pretty. So if you're building a supply out of these things, you probably want to do at least a modicum of output filtering would be nice. Bugger it, I decided to go to town. I just took apart my leads there, and now I've got the sense and the load leads going directly into the Phoenix contact connectors, and I've got much thicker gauge wire, really overkill, going to the input there, so we don't have to worry about the drop across there. The power shown here should be the input power, and absolutely, because we're doing the sensing, the output power shown here should be absolutely spot on. So, yeah, no worries. It was a bit how you doing before. Interestingly, the quiescent current here with no load changes when you turn the output off and on, even though there's no load. So it's 0.5 watts drops down to 0.39 with it with the output off. So we should actually include the on figure in the efficiency calculations, I think. Alright, so what I think we're going to see on the results for this thing is that it's going to be optimized because it's like designed, it's got bugger all heatsinking on it, and it's designed for like 70 watts output power capability or whatever it is. It needs to be like really high efficiency. Even like 90% is not going to cut it. So they're probably going to be shooting for like 95% or, something of the mid-90s. But you can't design, the problem with universal supplies like this, you can't design them to be universally efficient over the entire input voltage range and output voltage range and output current range as well. It's just not possible. So you've got to pick probably the worst case position like this, because where you could design your thermals around, the worst case condition of like the maximum output voltage driving the maximum output current, i.e. that's 70 watts, the power delivered, worst case. They're going to design around that. So I expect to where its maximum power delivery capability is where it will be most efficient at 90 to 95% efficient or something like that. And then at lower output voltages for the same given input, I'd expect it to be lower efficiency. So say you've got, 30 volts input, and then you, like for 20 volts out, you'll get an efficiency curve. And then if you do 5 volts out, it'll be lower efficiency again. So that's the sort of results we expect. That's just how things are with DC to DC converters like this. They're always a compromise, and they always basically, as buck converters like this, basically have the same characteristic trade-offs. Right, so I finished a sweep at 5 volts. I got basically the input power and the output power from 0.1 amps up to 3 amps, basically. And I just noted, right, I was just going to do the sweep again for a 12 volt output here. And you'll notice that the quiescent current, well, the quiescent current remains the same. If you switch the output off like that, it's not the exact same 0.390 watts. So that's the electronics in there. As I said, that's not going to change, but you switch it on with absolutely no load at all, and it's 0.6, whereas we're getting 0.5 before. So that's all part of the efficiency of this thing. And after laboriously measuring and plotting, or entering and plotting the data, this is what we get. Ta-da! We have our efficiency curve here for the DPS3003 power supply for a 15 volt input. And we have separate data for 30 volt input and 40 volt input as well. I didn't measure like a low input voltage, because like, what's the point? No one's going to have like a, a 7 volt input volt and a 0 to 5 volt power supply, but yeah, anyway, there's only so much you can measure. So this is our efficiency from 30 to 50%. I just sort of expanded the scale. When you plot things from 0, it kind of like just crams all the data up in the top, and you don't see as much detail. And this is quite interesting. Look at this. This is the, let's go in. This one here, the red one, is the 12 volt output. So 15 volts in, 12 volts out, and look at that efficiency. That was pretty much where I thought it must be. It's actually up like 96%, where I thought it kind of like had to be for right up to 3 amps. So I got 0 to 3 amps here. By the way, I measured 0.1 amps down at the lower end, because I knew there'd be that big taper down at the lower end and not much happening up at the higher end. So I did 0.2, and I did 0.75 here, which is an oddball one. And if you have a look in here, the chart type, I think I've done a video on this somewhere, is actually a scatter chart. It must be to then get the linear axes down the bottom here. It's kind of weird. I think Excel does the same thing. I'm using LibreOffice here. So yeah, otherwise it just linearly spaces the samples. So you have to use a scatter plot. Anyway, doesn't matter. Small little tech tip there. So anyway, that's very, very efficient. And as always, down at low currents, it tapers off, but it's still a respectable, 82%. And for 5 volts out with the same 15 volts in, it's still a very respectable 90% efficiency. Peaks it there. It's a little bit under, but that's hunky-dory. But look at this, for 1.5 volts out, for 15 volts in, it's not great. Look, it peaks at around 68% here, and like right up at the higher currents, it's pretty miserable, even though it's delivering a lower amount of power, right? It's still the 3 amps, but it's only at 1.5 volts, right? So 4.5 watts, as opposed to up here, which is, 15 watts for the 5 volt output one, for example. That's because, like I said before, the converters, you have to optimize them for a certain input voltage and input power and output power range, and you just have to live with whatever efficiency you get outside of that. And that's usually not a problem in product design, because if you're designing a switch mode converter for your product, for example, then you know how much power your product's going to take, as long as it doesn't drastically change power modes from one to the other. Of course, you know how much it's going to take, so you optimize your DC to DC converter design efficiency for that particular current. You size your inductors, you size your, your transistors and whatnot, and for that particular configuration. But on a universal power supply like this, there's just really not much avoiding this unless you go to great complexity and great expense. Spared no expense. You're gonna just have to put up with a poor result like this. Now, here's the interesting bit. What we really care about is how much power does this thing dissipate. So what I've had to do, right, I've deliberately kept this one a bit clean, but here's one I prepared earlier. Here's the exact same graph again, but I've included a second y-axis on the side here, this secondary y-axis, and this is the power loss, the power dissipation in the module. So that is from 0 to 4 watts, and that's what these dashed lines here, the colors represents the exact same. So red is 12 volts out, red is 12 volts out here. And this is, you'll find these in some data sheets as well. They'll do power dissipation loss. So this is how much is dissipated. And here's the interesting bit for the, say, the 12 volt output, right, which is delivering the most amount of power, 3 amps times 12 volts, so 36 watts output power, right, which is quite a lot for such a little module, right? It's only dissipating at worst 2.2 watts there, and of course the heatsink in there, it's sized up. It might be, maybe it's 5 degrees C per watt or something like that, so it might raise 10 degrees, which is kind of what you feel if you stick your fingers on the back of those things. So guesstimate, ballpark, it's probably a 5 degrees C heatsink, 5 degrees C per watt heatsink, right? And it's not too dissimilar for the 5 volt output, the blue line there, which is what you'd expect, because they're a similar sort of efficiency up here. They're both plus 90%. But look at the loss in the 5 volt one. Now the 5 volt one is only delivering 1.5 volts at 3 amps, so it's only 4.5 watts as opposed to 36 watts, so it's delivering much less output power. But look at the power dissipation. This green line going up here. It is now, even though it's delivering, right, less than an order of magnitude, that little module has to dissipate 3.8 watts. So there you go. They're the trade-offs when your efficiency drops like that, because it's not an optimized, can't be an optimized design almost by, the nature of DC to DC converters trying to deliver a full range of output power. You just can't get it. So it actually dissipates more power and heats up more, delivering a lesser load. And that's exactly what you'd expect. There's nothing surprising here. This is basic DC to DC converter stuff. And by the way, that power loss includes the quiescent loss of 0.39 watts. So even though it's not necessarily being dissipated in the output transistor, the output diode, the output inductor, and that sort of stuff, the power devices that deliver your output load, it's still part of the module, so the module's going to heat up. So I think it's, it's a good thing to actually include that in your total module power loss, because that you could label that module power loss, for example. So there you go. Interesting, huh? Now we've done exactly the same thing again for a 30 volt input this time instead of a 15 volt input. So double. It's not quite up to its maximum. Its maximum is 40. And as you can see here, efficiency, once again, we've got different output voltages. We've got 24 volts this time. We've got 12, that's in the green, 12 volts in the red, and the blue is 5 volts. And once again, I didn't do 1.5 here, but if you did, it'd be, horrible, like down in the 60% probably, just like last time. So very similar, but we're getting a similar result. Like once again, that 95 odd percent right up there. Does it hit 96? Like it's pretty darn good. Exactly where you'd expect it to be for this type of, you know, small heatsink module that we've got here. It's fairly respectable at 5 volts out, but unfortunately the power losses are bigger this time with the 30 volt input. That's just the nature of the beast. And they all track fairly well, even though the 5 volt one output here is quite lower efficiency at under 80% here, right up at the 3 amps. They all track very well, so we're getting about 4.5 watts maximum dissipation at the full 3 amp output current. But once again, that the heatsink on it is like, it doesn't get hot. It doesn't get too hot to touch. It does an adequate job of doing this. And why not? Let's do 40 volts input. Only 2 output voltages the maximum, which is 32 volts. That's the red one there. Once again, we're talking, you know, that same 95%. Obviously, they've optimized it for that output power level, and once again it drops, you know, it tapers down. It's pretty horrible at the low currents here for the 5 volts out, but looking at the power dissipation here, there's obviously a couple of little oddball values in there. They're probably just typos. This should be, you know, fairly flat. There shouldn't be little spikes and things like that. The efficiency is pretty horrible right down here at low currents, but, you know, that's the problem with designing these wide range converters, as I said. But once again, you're at low output current, so the efficiency doesn't matter, so you're not dissipating much power. Once again, we're under 4 watts there for those sort of for those two particular 5 volts and 32 volt output from a 40 volt input. So there you have it. That's some characterization of the DPS3003 power module, and it's a really neat little unit. Noisy as all buggery, but, you know, add some filtering or something like that if you're concerned about that sort of thing. But it basically does what it claims, full voltage and current with 96 watts output capability, and it does it with basically that tiny little passive heatsink, because it really is, you know, quite efficient. And if you really want to push it to its extreme limits, we haven't characterized every extreme limit here, then you might have to have a bit of forced airflow, but that's a winning little module for like, what, under 25 bucks delivered or something like that. Absolutely crazy. Yeah, maybe I'll do like a reverse engineering of that and see what's doing in there. We know it's the, what is it, the XL7005 converter chip or something like that, but it's going to be using an external MOSFET, and, you know, external MOSFET because it's not built in to do that sort of jazz. But anyway, that is a really neat little module, neat designed, and it basically isn't lying in the specs. I rather like it. So there you have it. I hope you enjoyed that. If you did, please give it a big thumbs up. And at the end of this video, I'll link in, yeah, it's somewhere up there, somewhere. Yep, all over the place. Some other power supply videos measuring, I've done one specifically on measuring the DC to DC converter efficiency and all sorts of stuff. Linked in. Watch them if you haven't seen them. I've got tons of power supply type videos. Anyway, hope you enjoyed it. Catch you next time.